This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. So now that we've looked at objects, types, and values in some detail, we're going to now shift our focus to operators and expressions in the language. In the C++ programming language, there are many operators, and this slide and the next few slides identify or list all of the different operators. So to begin with, we have the arithmetic operators, things like addition and subtraction and multiplication and division and the remainder after division, as well as a few other things like incrementing operations, which basically add 1 to a value, decrementing operations, and so on. We also have bitwise operators, which perform operations on bit masks, or integers represented in binary form. Next, we have assignment and compound assignment operators. Probably one of the most important operators in the programming language is the assignment operator, in other words, equal sign, which allows you to assign the value of one variable b to another variable a. Then we have what are called compound assignment operators, which are essentially assignment operators that are also combined with some other computation. So for example, the addition assignment operator, which is plus equals, essentially what this does is it takes the value of b and adds it to a. So something like a plus equals b is equivalent to a is equal to a plus b. It simply adds the value of b to a. And then we have similar sorts of compound assignment operators for subtraction, multiplication, division, and so on. You might wonder, what's the point of having compound assignment operators? Because we can always write things as two separate operations, an assignment and whatever other operation is going with the compound assignment operator. The reason for compound assignment is sometimes we can write more efficient code by using a compound assignment operators. We can essentially combine two things into one, and by doing this achieve more efficiency. Next, we have logical and relational operators. These are things which basically allow you to test certain conditions, like for testing for equality, testing for inequality, testing for greater than, less than, greater, equals, less or equals, not, logical and logical or type operations. Then we have member and pointer operations, things like array subscripting, indirection, also sometimes called dereferencing, which we talked about a bit earlier, the address of operator that we talked about earlier, and various different member selection operators, which we'll talk about in more detail later on in the lecture slides. And there are yet more operators. I won't talk too much about the ones on this slide. The function call operator is probably the most important one, at least in the near term. Some of the other operators we'll talk about as we go much later into the material for these lecture slides. And lastly, we have a few other operators. Most of the operators on this slide relate to types, typecasting, and exceptions. And most of these things are associated with more advanced programming. So a lot of these operators we won't talk about until much later. Two properties of operators that are quite important are precedence and associativity. So what's meant by precedence, if you think back to your elementary arithmetic days when you're first learning how to add and multiply, you'll recall that you have to perform multiplication before addition. In other words, this is the order of operations for arithmetic. And operator precedence is basically carrying this idea over to programming languages. In programming languages, you have many other operators other than just multiplication and addition, and you have to know what are the order in which these operations are applied. So higher precedence would be applied, operations would be applied first. Also, there's the notion of associativity. So if you have several different operators that all have the same priority, then you need to figure out in what order do you handle those operators. And there's two different types of associativity, either left to right or right to left associativity. Left to right simply means that if you have a whole bunch of operators that all have the same priority, you evaluate them in left to right order as they appear on the page. For right to left associativity, you evaluate them from right to left. And on this slide, we have the two highest precedent classes of operators. The column here that indicates precedence with a number, lower numbers are higher priority or higher precedence. And the table continues on this slide and continues on for several more slides. And again, the table continues on this slide. I'll make a few comments with respect to some of the operators that appear on this slide. what's particularly noteworthy here is that multiplication and division have higher precedence than addition and subtraction. And any reasonable programming language would have this property because the laws of arithmetic say that multiplication should have higher precedence than addition, and therefore you would want this to carry over into any programming language as well. Also note that the multiplication and division as well as addition and subtraction operations are left to right associative. So for example, if I say a plus b plus c, because both of the plus operations have the same precedence, the precedence doesn't tell you which one would be evaluated first. But if I say a plus b plus c, because it's left to right associative, the addition operation, it would first add a plus b because a plus b appear to the left of c. So it would add a plus b first and then add c to the result. And again, the table continues on this slide. And finally, on this slide, we reach the end of the table. And perhaps the one thing that's worth noting here is that the assignment operator, notice that the assignment operator has a very, very low precedence. It's almost at the very end of the list. And also note that it's right to left associative, not left to right associative. It's an example of a right to left associative operator. So if you write a equal b equals c, it first evaluates b equal to c, and then evaluates a equal to the result of b equal to c. Some of the operators in the language can be written in more than one way, and the table on this slide just shows some of the alternative spellings or tokens that can be used for some of the operators in the language. So for example, the logical AND operation can be written as AND, or for example, the bitwise AND operation can be written as bit and so on. On this slide, I need to introduce a few basic concepts from the C++ programming language. The first is the notion of an expression, and the second is the notion of a constant expression. So an expression is just a sequence of operators and their operands that specify some computation. For example, you might write something like 1 plus 1. This is an expression in the language. There's an operator plus, and then the operands, which are 1 and 1. Every expression has a value and it has a type, and I'll go through an example in a moment to explain this in more detail. The other notion or concept I need to introduce is that of a constant expression. And a constant expression is an expression, not surprisingly, but specifically it's an expression that can be evaluated at compile time. In other words, the value of the expression, the result of the expression, doesn't require any knowledge that's only available at the time the program is run. It only requires knowledge about information that's available at the time that you're compiling the program. So an example of a constant expression would be 1 plus 1. It's a constant expression because this expression can be evaluated at compile time. When the compiler sees 1 plus 1, it knows that 1 is an integer literal of type int that has the value 1, and this 1 here is another integer literal of type int that has the value 1, and it knows that if you add an int with the value 1 to an int with the value 1, you get an int with the value 2. So this can be evaluated at compile time. 1 plus 1 does not depend on anything that happens when the program is running. It can be computed at compile time. So this is a constant expression. And on this slide, I have a few examples to kind of further illustrate the notion of expressions. So I have a little code snippet where I create a variable of type int called x and initialize it to 0, create a variable y of type int, initialize it to 0, create a pointer to an int, initialize it to the address of x, and then we create a double variable called d and we initialize it to 0.0. And then at this point, imagine that we evaluate a number of different expressions where the expressions that we're evaluating here at this point in the code are the expressions that appear in this table here. So for example, if we evaluate the expression x, this expression x has type int because x, the variable x has type int, and the value of this expression is 0 because x was initialized to 0, so the value that x has is 0. And for example, if we evaluate x plus 1, so if you imagine that we had a line of code that somewhere contained x plus 1 on it down below here, the type of this expression is int because x has type int, and when we add the integer literal of type int 1 to x, we get another int for the result. So the result has type int, and the result is going to be 1 because x is equal to 0, because in the code over here, x was initialized to 0. When we add 1 to it, we get a result of 0 plus 1, which is 1. So the value of this expression is 1. So again, each expression, it has a certain type associated with it and a certain value. At this point, I'd like to make a few comments about the logical and logical or operators. So first of all, the logical and operator, which is denoted by the double ampersand. The result of the logical and operator, which takes two operands, the result of the logical and operator is true if both of the operands are true and false otherwise. And what's important to understand about the logical and operator is in the case that the first operand evaluates to false, the second operand is not evaluated. And the reason for this is if the first operand is false, it doesn't matter what the second operand is, the overall result of the AND operation is false. So in the interest of efficiency, C++ guarantees that the second operand won't be evaluated in this case because there's no point to evaluate it in the sense that it won't affect the final result that's obtained by the AND operation. Then in the case of the logical OR operator, which is denoted by a double vertical bar, it has, just like the AND operator, the OR operator has two operands, and the result of the OR operator, the logical OR operator, is true if either operand is true and false otherwise. And what's important to understand about the logical OR operator is in the case that the first operand is true, the second operand is not evaluated. Again, this is guaranteed by the language. And the reason for this is efficiency, because in the case that the first operand is true, it doesn't matter what the second operand is, because true or anything is true. So the result has to be true if the first operand is true, regardless of what the second operand might happen to be. And this behavior is sometimes referred to as short circuit behavior, or short circuit evaluation. And this is illustrated in the example below. So we create an integer variable x and initialize it to 0. And then we proceed to evaluate a Boolean value, in other words, a true-false value. And we're initializing it to the parenthesized expression on the right of the equal sign here. And we have a logical OR operator here. And the first operand is testing if x is equal to 0. And the second operand is incrementing x, essentially adding 1 to x, and then checking to see if x is equal to 1. And in this particular case, the first operand of the logical OR operation will be true because we just initialized x to 0 on the previous line, so when we test if x is equal to 0, this will be true. And in this particular case, since the first operand is true, the second operand won't be evaluated. So in other words, the plus x equal 1 will not be evaluated. And the reason why this is important in this particular piece of code is that this second operand actually has a side effect. Evaluating this expression will increment x, but because this doesn't get evaluated, x won't get incremented. So on the next line where this comment appears, if we actually printed out the value of x, x would still be equal to 0 and also b would be true. Then if we continue on to the next line in this example, we then proceed to check and see if x is, well, we're using a logical AND operation here, and then we proceed to check and see if x is not equal to 0. Well, x is equal to 0 because we initialized it to 0 up above and we haven't changed it, so this will evaluate to false. And then because this is a logical AND operation and the first operand is false, the second operand won't be evaluated. So even though the second operand has the side effect of incrementing x, because the second operand is not evaluated, x will not get incremented and it will still be 0. So on the next line where this comment appears, if we printed the value of x, we would still have 0 being printed for x, and the Boolean value b would be equal to false. So again, this sort of behavior is referred to as short circuit evaluation. In code, sometimes the need may arise to determine how much memory is required by a particular type or a particular object or expression. And for this purpose, the language provides an operator called the sizeof operator. And the way the sizeof operator works, if you have some type t, you can write an expression that looks like size of and then in brackets this type name t, and this will return the number of bytes in memory that's required by that type. So for example, you could say size of int, and the value of this expression is the number of bytes in memory that's required to store an integer of type int. You can also use size of with expressions. So if you have an expression, for example, you have some variable x and you've taken the address of x and you want to know how much memory is required to store this address of x, this result, which would be a pointer to x. You can say size of and then ampersand x, and this expression would give you the number of bytes required to store that particular result. A few other things about size of. In the language, size of char, signed char, and unsigned char are guaranteed to be 1. In other words, char, signed char, and unsigned char always take 1 byte in the language. A byte, however, is not necessarily 8 bits. It's at least 8 bits, and probably on most mainstream architectures it is 8 bits. On some more exotic platforms, though, it may be something larger than 8 bits. Earlier we talked about the const qualifier that can be used to modify a type and essentially indicate that a variable can't be changed. The const qualifier expresses a notion of constantness or immutability of a value. Related to this qualifier is another qualifier called constexpr, or spelled constexpr, and this qualifier indicates that the object that's associated with this qualifier has a value that's a constant expression. In other words, it's an expression that can be evaluated at compile time. Now, constexpr implies const. So in other words, constexpr is a much stronger condition than constness. It basically means not only can something not be changed at a particular point in time when the program is running, but it also indicates that it's so constant that you even know what it is before the program starts to run. In other words, it only depends on information that's available at compile time. So for example, we might have an integer variable x, int x, and we add this constexpr in front of it. What this says is that the value that x is equal to is a constant expression. And clearly 42 is a constant expression. The value of 42 is known at compile time. It's simply the value of 42. It can't possibly be anything other than 42 because it's a literal constant. And down below we have a few other examples to help further illustrate constexpr. So here we create an integer variable x that's a constant expression equal to 42. Then we create a regular int variable y and initialize it to 1. Then we try to assign a value of 0 to x. We can't do this. This will generate a compile error. The reason why is because x is a constant expression, it's implicitly const. In other words, its value cannot be changed. So we're trying to change on this line something that's constant, and we can't do this, so this is a compile error. The next line is okay, however. In this case, we're creating a constant reference to an integer called x1, and this x1 is bound to the integer x. In other words, it's initialized to refer to the variable x, which is constant, but that's okay because the reference is also referring to something that's constant, so we can't use the reference to change the variable that is constant, so this is okay. And for similar sorts of reasons, this next line is okay. On the next line here, we have a bit of a problem. This will cause a compile error. The reason why is in this particular case, we're trying to take a non-constant reference, in other words, a reference which refers to something that's allowed to be modified. So in other words, x2 is allowed to be modified, but we're trying to bind this reference to a variable that's constant. Because up above, if we look at the definition of x is a constexpr variable, meaning it's const. Well, implying that it's amongst other things that it's const. So x cannot be changed, but we're trying to bind a reference to x that would allow x to be changed. So this would generate a compile error. And for similar reasons, this next line will also produce a compile error. Here we're creating a pointer to an int called p2. But this pointer, we're allowed to modify the thing that the pointer points to because there's no const out in front of this int star, meaning that this is a pointer to an int that's allowed to be modified. So if this line of code compiled, because we're assigning this pointer to point to x, because we're assigning p2 the address of x, we could then dereference this pointer and change whatever the pointer points to. But this would allow us to modify something that's constant. Therefore, this is not allowed by the compiler. This will generate a compiler error. If you go on to the next line here, this is okay. We're creating an array of integers called a1, and we're saying the size of the array is x. This is okay because the size of the array is a constant expression. X is actually a constant expression. And in the language, in C++, the size of arrays always have to be constant expressions. The next line, however, will fail to compile because in this case, y, if we look up above, y is not a constant expression. It's just a regular integer variable. Therefore, we cannot create an array with a size that's not a constant expression. This will generate a compile time error. And the reason for disallowing an expression that's not a constant expression in the brackets here, in other words, not allowing the size of the array to be something that's not a constant expression, is mainly to simplify compilers and make them easier. Some compilers actually do support variable length arrays, but this is not actually required by the standard, and actually, technically speaking, it violates the standard if compilers do this, although some of them do. In any case, you probably shouldn't rely on non-standard behavior from the compiler. When writing code, it's often advisable to include a number of self-checks throughout the code in order to ensure that the code is behaving as expected. This can be useful for detecting bugs. There's two times at which you might want to perform such checks. One is at compile time and the other is at runtime. For the purposes of doing compile time checks, the language provides the static assert statement. So the static assert statement has two arguments. The first is a Boolean constant expression, which is the condition that you want to test. And the idea here is that the condition that you're testing is a condition that should be true. If it's not true, this would be an indication that something is seriously wrong with the code. The second argument to static assert is a string literal for an error message to be printed if the condition you're testing fails to be true. Again, the idea being that if the condition that you're testing with the static assert fails to be true, it's an indication of a serious software problem, and therefore the compilation should stop and print some error message. And this string literal is the error message that would get printed. So just as an example of how static assert might be used, the first line here in the example is probably the more practically useful one. Suppose, for example, that your code is using the type int for a number of key variables, and you know that if int is not at least 4 bytes in size, there's going to be issues that int won't be able to represent values with a sufficiently large range that your program can work properly. So rather than having the code just mysteriously fail due to the problem that int is actually not big enough because your code has made some assumptions that ints are at least 4 bytes, instead you can add a line like this first line here into your code, which will basically enforce at compile time that size of int must be greater or equal to 4. So when the compiler sees this first static assert line, it will check this condition, check to see is size of int greater or equal to 4. If it is, everything is fine and the compilation continues. But if this condition is not true, instead it will print the message int is too small and then terminate the compilation with an error.